In my videos, I make bold claims and leave the evidential analysis to future David. Ah, sucker! But that is me. I am future David. Ugh. I didn't display a tech in my previous video, and there's a good reason for that. I finally chewed myself through reworking the library. Oh, yeah. And in this video I'll present to you my due diligence, the comparison, the showdown between an Octree and a Contree in my implementation. So bear with me because it's gonna get wild. First, I need to extend on some things after my previous video. And by the way, the rewrite makes the library conceptually incompatible with its current name, so Chocobox is archived, and long live Voxel hacks! If you have a few moments to start the repository, please do so. I won't profit from it, but it feels good to see it gathering interest. I mentioned complexity as a factor for performance, and while that is the case, it covers a deeper, more complex aspect of graphics programming I didn't really want to cover yet. Register pressure! Because also mentioned by a dear commenter, register pressure plays a very important role in performance. I'll describe what that exactly is in my upcoming short stack video, but in a nutshell, the more data GPU kernel or shader needs to store, the more registers it will occupy during execution. This is a bottleneck, and there are limited registers in the GPU. Even if the shader has lightning fast logic, the GPU can't execute as much pixels per frame as it would with lower register pressure.
Stop hoarding. I can't be more blunt about it.
Dear colleague and Voxel rockstar Gabe pointed out that there was a hole in my argument about the sizing inconvenience of the 512 trees. I mentioned the 5x5x5 cube and the cube of 4K, and the connection isn't completely sound without context. You see, inside the game engine there are objects of multiple sizes. Not everything is a single array for practical reasons. A vast landscape fits nicely into a big 512 tree. It's a good fit, because it has enough space for all of it. But a game is expected to have smaller objects as well, for example a small coin which can be 4x2x4. In the coin's case, the structure is not a good fit. The container can be a cube of 8x8x8, but not only there is wasted empty space, the overhead is the same for the small coin and the large landscape, which is a relatively big package to carry for such a small thing. The best thing would be to have different data types for different sizes of data, but
ain't nobody got time for that.
Ideally though, the best structure mostly depends on the data it contains. Right, I think I can move on now. Except if you still want me to address something, write a comment about it. I won't bite, I promise. Now, to see if my claims in the previous video were true, or I made myself an I compared the old implementation and the rewrite. For those of you now joining us, the library was rewritten to store data in 64 trees instead of Octrees. I made a video comparing these two data structures, link in the description. I'll also leave a link there for the exact changes. The best part is you can review everything, as my library is open source. Check it out, like literally, it's in Git. In fairness, there are some changes worth mentioning here that are totally irrelevant to the ray tracing algorithm. These were mostly data update changes and part of the GPU streaming logic. The former is totally irrelevant and the latter is only half relevant, as it's pretty easy to filter out, and even if it's not filtered out, it doesn't affect performance that much. Alright, let's look at them frames. Let's go! Just look at this beauty go! Numbers go! Like seriously, double FPS. What? Look at them puppies! It even looks good on the chart. And if you were wondering about frame time, it's more or less consistent. It went from 10 to 5 milliseconds.
Nice.
Another aspect of comparison is code complexity, which is a pretty controversial topic because you can't really equate the number of lines to depth of logic, but I can confidently say that with this rework, lots of overhead was indeed removed. Overall, 3,000 lines of code were added and 700 more deleted, so the codebase got smaller and in most cases it got simpler. I'm confident that the 512th tree rewrite will be even easier now. If...
No, God! No, God, please, no!
Also, binary file size got smaller by 17%. That's not a shock though, because the number of nodes within the data decreased significantly. Although this does show that the nodes themselves do not require a lot of space. While we are still at the topic of nodes, I mentioned there was a difference which is quite easy to filter out. The reason is exactly the number of nodes. I have implemented a custom raycast based GPU streaming system which copies the data in view to the GPU in real time. You could already spot this in action if you paid attention to the
turquoise.
The light blue shade, as missing data is marked with that color. Because the 64 tree based implementation has considerably less nodes, the same information can be streamed to the GPU with less data. This shows in the video, but I also marked this in the FPS chart. In conclusion, if you want better performance for your own engine, use data-appropriate structures. For my purposes, that was the 64 tree. That was about it for the comparison. Could have gone deeper, could have investigated more, but this seemed like a good enough presentation. It was quite challenging to visualize too. If you want to go deeper, you can always dive into the code. Look for me on Discord, write a comment, interact. It is great to see my videos gathering some interest. I'll hope to keep this up, but do tell me if I'm not going in the right direction. Tough love is always welcome too. And lastly, thank you for watching this. I appreciate it. Bye.